Okay, good afternoon, everybody. Happy Wednesday. So a couple quick announcements. First off, midterm is rapidly approaching. Remember, it's on Tuesday, February 11th, so that's not Tuesday, that's next Tuesday after that. If you haven't done so already, start thinking of this point that I mentioned on Monday. I would like you guys to participate and design a Piazza question to go on the midterm. Again, we do this for two reasons. One, if you guys create a question, also create the answer, but the purpose of doing this exercise is I want you guys to think about a kind of question that you think is on par, on level. Creating a question is one way for you guys to practice how to ask questions and understanding the material you have. So this is an exercise I want you guys to engage with because it's a great way for you to help to start test each other. Second, based on the questions that are placed up, I guarantee I will pick one of them. It will be on the midterm. So this is a chance for you guys to participate and practice. If you have 50 questions get submitted and 50 get practiced, one will still make it onto that point too. It's a way for you guys to see and practice the material ahead of time. So please do engage with it. We'll see what happens there. Again, if it's a completely wrong question and your answer is completely garbage, I will say though. And so I will not lead this as a complete open, but it's a way for you guys to participate in that part. So please do step in. Okay, last class. We gave you guys the introduction to the carboxylic acids, their basic properties. This is mostly a reminder of why carboxylic acids are acidic. Remember, this is resonance. This is how we use things like pKa to rank the relative acidity and stability in that system. And we start talking about how we make them. We covered oxidation reduction, so these are just adjustments from our primary alcohols, how we form and how we break them down. We also broke out nitrile hydrolysis. This is where we've taken and reformatted on the same oxidation state. This is we're starting off with something that is a carbon triple bond nitrogen, and we're adding water to get to a carbon 3 oxygens, but still it's a different presentation. So, review. Again, quietly first. Let's see how you guys do. Rank these in terms of their acidity. Lowest pKa, most acidic is 1, highest is 4. Take a minute. Let's do this as a speed drill. Okay, turn to the person next to you. What is the pKa of each one? 1, 2, 3, 4. Why did you choose that one? Okay. Time. Okay. Let's find compound number 1. Now again, if you're working through these and you're given a presentation of multiple compounds, very, very good thing to do is do this not as find one among 4, reduce it to binary comparisons where you've got sort of a head-to-head. And that way you can easily rank them as above or below. So even if you kind of get sort of an individual number wrong, if you're asked for sort of relative ranking, you can probably sort out the order based on I know X is lower than blah, and that way you can sort of help to rationalize pieces out. So give me which one of these is the most acidic, lowest pKa. Which one of these is your number 1? What functional group? Carboxylic acid. That's going to be this one. Everybody agree? Yes, that's going to be number 1. This is your carboxylic acid. And again, we're isolating and saying you're deprotonating from where that proton is. What's the rough pKa of a carboxylic acid? 5. Good. All right, next. Who is the next most acidic proton? If you had to name it as a function group, what do you got? The alcohol? phenol specifically, but let's step it back. What is the pKa of an alcohol, an OH deprotonating it? Is how does it modify when you've got aromaticity help you out? So 16 is about normal, but then you get the aromaticity bump, it's going to drop to 9, 10, lower, right? That's not just an alcohol, it's a more acidic alcohol. So it's not as good as a carboxylic acid, but yeah, that's going to be number 2. Got it. Which is next? Carbon as an acid or nitrogen as an acid? So I got some carbons and some nitrogens. What's the pKa of this? This here, deprotonating that center gives you an enolate, right? This is your alpha proton. So what would you about? What's the about pKa of a proton next to a carbonyl? Standard ketone, standard aldehyde is about 20. Yep, that's a good range. 20, 25, not bad. What's the pKa of this nitrogen? 36, nuts, right? That is the conjugate acid of one of our favorite bases. That's LDA, right? Lithium LDA is that nitrogen minus with a lithium. This is what you form when LDA rips a proton off. That is a ridiculously good base. That's a very, very bad acid. Now, one of the number of things that people hit here is like, wait a minute, you said nitrogen has a pKa of 5, 10. Where is that true? If I'm talking about the acidity at a nitrogen type center, I am not talking about nitrogen neutral. I'm talking about protonated nitrogen. Remember, what I'm showing you here is this molecule is the acid. I'm removing a proton from that neutral molecule to make nitrogen minus. If this was NH2 plus dialkyl, yeah, that is the protonated nitrogen. That's a different acid. Its conjugate base would be this molecule. When this is an acid, its conjugate base is nitrogen minus, right? So there's two different, think of it as a diprotic acid in that case, right? You got to move up two stages. Good. So today we're going to continue talking about other ways to make or break carboxylic acids. We gave you guys a couple of different systems last time, and the way we tried to break it down this time is into these kind of 4 general approaches, highlighting both how you might make the carboxylic acid and at the same kind of genre, how you might break it. We talked about oxidation, so starting from carboxylic acids, this is where we use things like PCC, Jones reagent to form the carboxylic acids, and then the reductions. Remember, what is the only reducing agent you guys are allowed to use to knock out carboxylic acids? You can use lithium aluminum hydride. That is your choice. Why can't you use hydrogen over palladium? Hydrogen over palladium selects for what kind of bond? Alkenes, right? Those are primarily here. This guy, you need the big dog. You need lithium aluminum hydride. The other one is nitrile hydrolysis. That's starting from a nitrile to form here. Again, the thing I tried to highlight last time, this is not an oxidation reduction reaction. You're starting from something with 3 heteroatoms, nitrogen triple bond, to 3 heteroatoms, 3 oxygens, just 2 doubles and 1 single. But you're at the same oxidation state. Now we're going to talk about these ones. What's unique about approach 3, approach 4, this is where we're doing manipulations on the carbon bonding skeleton. We're adding carbons or subtracting carbons to make your carboxylic acid. So think of these two, you're reformatting the carbon skeleton, versus down here, now we're actually breaking or forming bonds to bring in the carboxylic acid. That's why I've tried to organize it this way. Okay, how we form carboxylic acids using Grignards and alkylithiums. This is where we use CO2 as our electrophile. So what we're doing here is I start with a nucleophilic carbon, either lithium or Grignard. I use CO2 as my electrophile. Think of CO2 as just a carbon double bonded oxygen. That is a carbonyl compound. And this nucleophilic carbon can attack CO2 to make your structure. The useful thing here is this carbon here, this center, is that carbon here. This CO2 is that carbon here. We have made this bond, carbon to carbonyl. That's the new bond we just formed, so we've elongated the carbon skeleton by 1 bond. That's the thing that makes this part unique. We've added the carboxylic acid to the party. We haven't reformatted the carbon. That matters for different types of molecules you're building. Same thing for Grignard. You form the Grignard. That's my nucleophilic carbon. There's my CO2. CO2 ends up carbon here. Nucleophilic carbon is this fragment. You're making this carbon to carbonyl bond. That's the bond that you're actually forming between these two. let's see if I can go to my pointer. Sorry, today, so on Monday over the weekend I had the plague. Today my iPad has the plague, so we're going to have to do it this way. That carbon right there came from CO2. This carbon came from your Grignard. That's the new bonds you form. So that's how you form them. Very simple reaction. Don't worry too much about the mechanism. It's similar to how you take a Grignard to attack a carbonyl, right? It's nucleophilic attack. Electrons go up. There's your new carbon. Nothing big. The other side, though, is possible. We can do, from a carboxylic acid, we can also eject CO2. This is what we call decarboxylation. So the two reactions as a pair, making carboxylic acids, carbon minus plus CO2 gives us the carboxylic acid. On the other side, we can lose CO2 to give us back our alkane. So we can break out CO2 as what we call a decarboxylation. This is simply done with just heat, but the important thing about these, there's a very specific type of molecule that allows us to do this decarboxylation. It is these what we call beta keto acids. So what's important about this structure, the decarboxylation I'm showing you here only works when you have a substrate that has carboxylic acid, some alpha center, and then on the, remember, alpha to the carbonyl we're talking about, that's this one. One more over, we call it beta. This is the beta carbonyl here. If you have a beta keto, that's what we're saying here, acid, these are very prone to mild decarboxylation. So just as long as they're protonated, they have to be under the carboxylic acid state, not carboxylate, not deprotonated. And just a little bit of heat, you can easily kick CO2 out of this group. This is a very easy, mild treatment to break CO2 out of a system. This is synthetically useful. We use it for a bunch of other things, and we'll come back to it later, because look at your product. The way that this reaction works is actually a very special, what we call pericyclic reaction. It involves a six-membered ring where you've got the carbon-oxygen, the hydrogen-oxygen bond here is promoted over. That's making this new carbon-oxygen bond. That's reforming the CO2. The carbon-carbon bond you have here, we're ejecting that over. So we're breaking this sigma bond here, and we're forming a new carbon-carbon pi bond. And the last one, this carbon-oxygen pi bond, bumps over, and you get a hydrogen-oxygen bond. So it's a pericyclic reaction. That's what makes it possible and special. It requires all 6 electrons in what we call a concerted reaction. That means that all 6 happen in one transition state. On top of it, you need this geometry. You need 1, 2, 3, 4, 5, 6 atoms in this presentation to allow this to happen. It has to have this exact structure. So everything you see here needs to be present. You end up with this enol form, which also means you got to be able to form an enol. If there's a structure that you have that for some reason making that carbon-carbon double bond is impossible because of geometry or substitution, this decarboxylation can't happen. So let's look at these two. If you were to warm these up, the question is, would they give you decarboxylation? What's the product of these two components if I actually carry out a decarboxylation reaction? Okay. So on this first example here, you guys should recognize this as carboxylic acid, carbon-carbon bond, carbon-carbon bond, carbonyl, alpha to my carboxylic acid, this center here. I have a hydrogen. That's good. Next, I've got this ketone on my beta position. This one is set up to do your beta carboxylic acid deprotonation or elimination. This one, you've got the carboxylic acid, 1 carbon away. This is the alpha position. I have a carbonyl there. This is not one that can do decarboxylation. So does everybody agree with that part? Just in terms of presentation and components. This guy here is in play. You will be able to get the decarboxylation happen here. This one, No bueno. You do not have the right setup to do this, this structure. What I'm going to try and do is jump over to my iPad so I can draw out what I mean. So let's just go through this example. So if you remember, in order to do the decarboxylation, we need carboxylic acid, and that needs to be adjacent. We have an alpha center and then a beta carbonyl. So it's that system. More importantly, it's this hydrogen, oxygen, carbon, 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 oxygen. So that's 6 atoms that make up the key transition state. So we've got that kind of contained here. To make it clear, the rearrangement that kicks out CO2 involves, again, I'll just circle it, it's these pieces here. We want it in a pericyclic or a 6-membered cycle. So I'm going to redraw it as the tautomer, where that part is a little bit more explicit. And let me just draw the rest of the molecule. So what I'm trying to highlight there is we have this hydrogen, we're going to go that atom number 1, 2, 3, 4, 5, and 6. That's the transition state that we need to be set up at. And when this reaction happens, what we're doing is we're getting the pi bond from the oxygen. It's going to pick up the proton. We're going to get a transfer, which is reforming this carbon-oxygen pi bond. And then we are breaking the bond between carbon-3 and carbon-4. So when we do that, what we're going to make in the end is a new carbon-oxygen bond, and just to keep the color coding the same, that's our CO2, and we've got a double bond between what used to be carbon-4 and carbon-5, and let me just fill in the rest of the molecule. Now for the numbering scheme, this is hydrogen, that's our number 1, that was number 2, the center here, that's our number 3, 4, 5, and 6. So just map out those different centers. What started off as this carbon right here, that was carbon number 3, has become the center here. So we've broken that bond, ejected CO2, and we have our final molecule. Now, if you notice in this structure, it's currently in the enol form. So that will rapidly tautomerize back to the keto form, which is going to be preferable. So the final product will be this keto form, where the rest of the molecule is just unchained. That gives us our CO2 extrusion. In the second example, we have the carboxylic acid, but we have a alpha carbonyl, not a beta carbonyl. Because of that, we can't form this 6-member transition state. The arrows, if we tried to draw them out, what you'd notice is it's not quite set up for the same kind of rearrangement. So let me just redraw that really quickly, trying to sort of emphasize that component again. So if we took our OH in a similar way, kind of lining it up, almost like our previous example. So once again, if we tried to, okay, I'll form a bond between there, I'm going to break this bond here. Now what you're leading to is this kind of weird intersection where you're both forming and breaking the bond in this one transition state. That's this kind of thing where you're getting this kind of fireworks happening, both arrows departing and arriving is disallowed. If you're ever drawing the mechanism and you're ending to something where like arrows are bumping into each other, it's a good sign that something has gone wrong. So this in particular is not the right geometry of the transition state, and as such of that, this will not undergo a decarboxylation. All right. So 3 more examples. I want to walk you guys through these later. These are the ones that you're going to do after the point, and like I said, I'll do these by pencast after the lecture.
So now for these problems, what we're doing again is identifying centers where we may have that carbonyl in a beta position to a carboxylic acid to allow us to have potentially a decarboxylation. So in this first example, it's set up very much like the previous. We have carboxylic acid. If we number these off, 1, 2, 3, 4, 5, and 6. That's set up in the proper sort of geometry. Notice again, we've got that alpha position as an sp3 center and this beta carbonyl. So if we were to undergo a decarboxylation, that would, let me just redraw that again in the more defined tautomer. So we're set up to really emphasize what might be possible. Like this. So we're going to do a pericyclic rearrangement, which is going to give us CO2 and our enol form of the product. Now, when we're done with that, remember that's going to tautomerize back to the keto form in this case, and then we're set up, actually once again, I'll just draw it like that, where we have another system ready to do another decarboxylation. So after that second cycle, we can do through the same point again. We're going to have another CO2 loss forming at least in between the enol, which then will come down to our final compound, which is just the cyclohexanone. So 2 molecules of CO2 can come out here because both left and right are accessible in this way. Okay, that's the first one. Now let's look through the second example. If you start off looking at it, it appears that it's set up similar to before. We have this kind of 6-membered transition state kind of lined up. We have all the atoms approximately the right place, but let's just draw this out. So if we, once again, we're going to line up the OH like this, double bond over here. Now what you can see is everything kind of looks right, but this step right here is problematic. Take a look at what you're actually forming here. If we draw out the arrows that we've given, what's going to happen is we've got our, looks like our enol form over here, and this arrow here is describing a double bond that's been formed between that carbon-carbon bond in order to lose our CO2. So what's happening here then is we're making a molecule with these 2 double bonds intersecting each other. If you look at the hybridization, specifically at this carbon, this is actually an sp hybridized carbon, which means it should be linear. And it is definitely not. When it's bent in a ring like this, it's forcing this sp center to be bent. It's the only way to get the 6-membered ring to work. So the ring strain would not allow this one to be formed. What's happening here is this center here, this is one of the other conditions that we have to pay attention to. That center there is sp2, and because of that, as it goes through the mechanism, it will change to an sp center. That's a result of that bond formation that we're going to do later on. Notice that these centers, where it does work productively, that's an sp3 center, which then becomes sp2 during the decarboxylation. So we need to look for an sp3 alpha center as well. Okay, so the middle one is not going to work. This last one here, now we've got 2 carboxylic acid attaching to the same carbon. It passes that test, at least we were talking about. This is an sp3 center, so that's okay. And notice we have our beta carbonyl, carbon-carbon bond, carbon, carbon, oxygen, hydrogen. So we have actually 1, 2, 3, 4, 5, 6 membered ring over here. Even though it's drawn geographically over here, imagine, remember this is like a spirocenter. Both of these are actually just spread out, but you've got 1, 2, 3, 4, 5, and 6 atoms there as well. So either of those 2 carboxylic acids could potentially eliminate, but let's take this forward. It happens sequentially, and you may actually see that both of them may not be possible. So let's do the first one. As drawn right now, it's kind of set up to allow us to draw that. So when we do that, again, I'm going to focus initially kind of what happened up here. This is where we now have our enol, right? We have a new double bond right here. We're still going to have one carboxylic acid attached. That's this group over here. And we still have the two double bonds we started out with. So to look closer, what we just did is we now have created an aromatic ring, right? Even though we're drawing the double bond to that, that outside presentation, this is actually what we just formed. So we've made an aromatic ring. So there's two things about that. Now that it's aromatic, this enol form is actually pretty stable. Because if you had to form it back to the keto form, like if it was going to tautomerize, what we would get is the keto form here. And let's say I'm going to draw it just so it's explicit in this form, and then the hydrogen right there. So this is the result of a tautomerism where we moved this hydrogen down to that center in order to give us back our keto form. The problem when we do that, though, is we paid pretty high price. We had to break aromaticity to do that, so we're going back to a non-aromatic. Yes, it's a conjugated compound, but we paid by breaking up our aromaticity. So this is really, really, really unfavorable. Forming this keto form is actually very difficult. As a result of that, only this first acid will eliminate. That's the only one you're going to lose is our decarboxylation. And the product is going to stop right here, both as the phenol, but also keeping this one carboxylic acid. So it's impossible to sort of push this second one out, because to access the keto form you'd have to break aromaticity.
So those are the two versions of how we use CO2 to make carboxylic acids. That's just a Grignard or like a negatively charged carbon system, a good nucleophile like a lithium or a Grignard, attacking or capturing CO2. That's how we form it. On the other side, if we have a beta keto acid under acidic conditions with a little bit of heat, we can do this decarboxylation. Those are those two possible geometries that you can form. The other one, approach number 4, is what we call the haloform reaction. This involves the enol reaction, the halogenation that we talked about before, and it really, really works best specifically with what we call methyl ketones. So your starting materials are going to be these ketone structures, specifically where you have a CH3, a methyl group in this position. So if you have these methyl ketone structures with bromine and base, you can generate this. Now remember, this is a multi-step transformation. If everybody looks at this, what are you doing here? Where does this remember? Back to that point we sort of talked about before. Where did we talk about this kind of a transformation? I take a ketone, I use base, I use bromine. How is that happening? What's the intermediate that's not drawn here to allow this to happen? Base, hydroxide, plus ketone. What's the first thing that has to happen? Yeah? Louder? Enolate. Negative here, picks up proton there. You actually make a carbon-carbon bond with an oxygen minus, right? That is nucleophilic on this carbon. This is an electrophile. When it pops down, you're going to add one bromine here, and you're going to still have 2 hydrogens left over. So yes, deprotonate that center. I'm going to nucleophilically attack my bromine. I'm going to add 1 bromine to that center. Now what? The 2 protons that are left over after a monobromination, so I've swapped these 3 hydrogens, it's now 1 hydrogen and 2 hydrogens and 1 bromine, I still have base. Those protons are more acidic than we started off, because by adding that electron withdrawing bromine, I'm going to allow to deprotonate those 2 protons much easier. Remember what we talked about is under acidic conditions, halogenation can stop at monohalogenation. Under basic conditions, stopping at mono is really, really, really hard. It'll go once, the protons are more acidic, it'll go a second time, the protons are even more acidic, it goes a third time. So this is 3 times. Each one of these carbon-hydrogen bonds will be sequentially replaced by making an enolate. Enolate grabs bromine, bromine gives you your product, proton deprotonates, new enolate, new addition, new enolate, new addition. So it's 3 individual steps as a cascade to make this guy. That's my tribromination. And again, why this happens specifically here, this over-halogenation, it comes down to the acidity of the protons that you've got, but the methyl ketone is special. Look at this molecule you've made here, carbon with 3 bromines on it. What you've now formed is this very, very stabilized carbon center. If we had to eject it, or if we had to do something that's going to form a negative charge on this center, all these halogens here are really, really going to help to stabilize that center. So the mechanism that we happen next, this guy here, this oxygen can come in and actually attack this center, and we can clip or break this bond between the two. So the carboxylic acid we're generating at this point, we're reformatting our carbon skeleton. First, what we do is we're adding 3 bromines to that alpha methyl center. We're turning it into a leaving group, and then we're ejecting this carbon as this haloform, or a bromoform in this case. It's Br3 hydrogen. That oxygen came from our basic conditions. Now again, this is not something you have to engineer. This is a consequence of the structure that you're dealing with. By starting off with these alpha methyl centers and doing this bromination under basic conditions, enolate will generate our tribromination. Once it's still under basic conditions and you've made this tribrominated one, clipping that bond is very, very, very easy. It's difficult to stop there. So this whole thing will actually reformat to your final component. In part of the lecture, the video for after class, I will draw out this whole mechanism for you of how you go from that oxygen attacking into here to eject this bromine minus. But this is the other way to kind of reformat the center using this haloform kind of reaction.
So I just want to add a little bit of detail to what we discussed in class. To show it explicitly, we start off with this methyl ketone, and we have strong or basic conditions. So when that happens, we're going to deprotonate that hydrogen, and we're going to generate an enolate. And when we do that, we have an electrophilic bromine in the system as well. So the enolate we generate here is going to be in the presence of bromine, which then is going to be attacked or labeled. So when that happens, now what we've got is our ketone and a single bromine attached to that center. So we're back to a ketone where we've labeled or exchanged one of those hydrogens for a bromine. If you remember back when we mentioned this in the previous lectures about this alpha bromination, these 2 protons are actually more acidic than the initial ones because we have this electron withdrawing bromine there. So it's possible to just go through a second cycle to make another enolate. This is actually easier the second time, and that's going to give us our bromine hydrogen, let's say. We still have extra bromine in the system, so it's possible to do second addition to give us now the di-substituted ketone product. So we're going to have 2 bromines, 1 hydrogen remaining on there. And as a result of that, this hydrogen is even more acidic, right? What made these guys acidic is that single bromine. Now we have 2 bromines present. That means that we can go a third time. And as a result of that, we'll make another enolate. This time, the dibromo enolate. And it's pretty easy now for that to pick up yet another electrophilic bromine from our Br2. That gives us our final tribrominated product. So in this first step here, what we're doing is swapping all 3 hydrogens for 3 bromines by going through this sequential enolate generation 1, 2, 3 times. And again, every time we pull off 1 proton and brominate it, the subsequent reactions get faster. So it's more facile after that. So that's the first thing. That's how we get to our CBr3 component. Next is to look at how we do this elimination. So once we're here, one thing I want you guys to notice, CBr3, if we just look at that, carbon with 3 bromines on it, that's kind of like if this was negatively charged, if this was something that we were to, let's say, break that bond and give those electrons like this back to that carbon center, we'd be making a carbon anion. That would be like this guy. And this is kind of a very special carbon anion. It's actually quite stabilized because we have 3 electron withdrawing bromines that's helping to pull that electron density out and away and stabilize this anion. So as carbanions go, this is a very special one. This is actually quite stabilized. You could almost think of it like a simple chlorine. In other words, this whole thing here is a leaving group. Because of that, we could take the hydroxide, we can attack the center, and then we can pop up to park the charge on the oxygen. So what we're doing here is the same sort of nucleophilic attack onto a carbonyl using a good nucleophile, hydroxide in this case, and we're going back to an sp3 tetrahedral intermediate. That's what this guy is here. So the tetrahedral intermediate, next move is to bring those charge back down, and now that we've got this leaving group, we're going to eject that CBr3, which gives us our carboxylic acid, and this CBr3 would be ejected as CBr3 minus. Now normally carbanion would be very terrible. We wouldn't want to have that as our leaving group. In this case, the 3 bromines on there stabilizes the anion enough that it's now facile. And again, you can kind of think of it as on the order of like a chlorine or something like that. It's a stabilized anion leaving group. Now that we've got this, it is basic enough to still pick off this proton, and that gets us our carboxylate and the bromoform. So the hydrogen we're showing there is picked up from this last step that you're showing here.
So if you look at these 2 guys, and we have to go backwards, let's try to make that specific molecule, the one we've shown here, this carboxylic acid, from the alcohol I started off with. Now, given the reactions I've given you right now, take a second. What's the strategy to do this? How might you go through this in the 4 different approaches I've given you? If that alcohol is your starting material, how might you make that carboxylic acid product?
So what we're doing now is just working through a process of trying to do a retrosynthetic problem. I'm trying to make this molecule from this starting material. And there's a couple key features that you should be noticing. So in this exchange, obviously the chemistry is happening here. That methyl center probably corresponds to this center here. What we have to do is somehow get rid of this oxygen. We're adding a carbon, but more importantly, the geometry that we're adding between these 2 centers is special. We have the same stereochemistry at both, where more importantly, it looks like there's an inversion that's happened at this center. So the first thing you should notice is oxidation. If you think of how we're making carboxylic acids, if I was just going to do a direct oxidation, that's not going to work because we have a secondary alcohol that'll make a carbonyl, not a carboxylic acid, so that one's out. We can't do simple oxidation chemistry. We have to add a carbon. So if we talk about adding carbon, you are doing one of the reactions we talked about today. This is where what we have to do is add something like either a carboxylic acid via CO2 or potentially maybe a nitrile. If you remember, those are 2 ways that we could possibly bring this piece in. So let's say we were going to use CO2 as the way to sort of add in. Remember, CO2 means that this would have to be my nucleophile. That's possible. We could do something like maybe I'm going to use PBr3. That would give me an inversion at that center and put in a bromine. And then now that I've got that, I could potentially use magnesium. Magnesium allows me to make the Grignard at that center. Looks like we're almost there. That's kind of like, I'm drawing this out as carbon minus MgBr plus. So I'm just emphasizing this is a carbanion at that center. And then that is going to add CO2. Remember, if I draw this, CO2 is an sp-centered thing. I'm just drawing it with a bend just for some little, so you can see the geometry easier. But it's like we're attacking that center to add our carbonyl group up here. Now the problem with that is this will work, you'll form the bond, but you have a planar electrophile, and the carbanion is functionally a planar nucleophile. You have two flat molecules that are being brought together. So when you do that, you'll make this one, but you will also make the other enantiomer. So the carboxylic acid will form both from the top and from the bottom because of attacking this from the top face or from the bottom face, effectively. So that won't work. You won't be able to go through just using a Grignard type mechanism to do this. And again, that's a consequence of trying to use a carbanion as your nucleophile. So what we have to do is think of it more like SN2 chemistry. Instead, what if we took tosyl chloride and attack on here first? Now what we've got is O-tosyl, so we've converted this oxygen into a leaving group, and we haven't touched the stereochemistry yet. Now we can come in step 2 with something like sodium cyanide. The sodium cyanide, remember that Cn minus is your nucleophile, and now that's going to be an SN2 reaction that's going to invert the stereochemistry at that center. What that's going to do now is give you a C-triple-N, and we've done this with a clean inversion of the stereocenter. We've set the carbon-carbon geometry that we're looking for. Now all we have to do is hydrolyze. So we can use something like HCl in water and heat, and we should be able to hydrolyze this without damaging that stereochemistry there. Now for this next problem, what we're trying to do is look at the conversion. You see we're starting from a tertiary bromide, and we are forming a carboxylic acid at that center. And we're looking at these two possible methods. So if you imagine you're going to do nitrile hydrolysis, do you think this is possible versus a Grignard and CO2? Really, this is one of those cases where we look at the question and it seems a little bit abstract, but if we said, if I'm going to do nitrile hydrolysis, that means I'm taking this molecule, I need to convert it into the nitrile. And what that would mean is I'm using Cn to then install that carbon and potentially make this first, which would then allow me to do nitrile hydrolysis. So there's nothing wrong necessarily with this step, right? If I could get this molecule, the hydrolysis should be possible. Instead, what I would say is the answer is no. This is not the problem. This is the problem. In order to install this nitrile, it happens via SN2 chemistry. And in this case, SN2 chemistry is forbidden on a tertiary center. There's no way we can do that nucleophilic attack. So this addition wouldn't work. Nitrile hydrolysis is not going to be the way that we're going to install that, that group. Reciprocally, if I'm going to do a Grignard reaction, that is going to be fine. If I took this and reacted with magnesium 0, I can do my MgBr, which is now a carbanion nucleophile. It's not a great one, right? But it will work, and that allows me to add 2 CO2 to give me my carboxylic acid. So this should be fine. Really, again, not super favored. It's a relatively sterically encumbered one, but if this is what we're going to build, that is by far your best one. Nitrile hydrolysis would require us to do an SN2 first.
So the last thing. So we've got those 4 different categories. Those 4 categories I presented you are your ways of either making or using carboxylic acids, right? We've got the sort of class 1, 2, 3, 4. There's one more special one I want to bring up. That's what we call the Strecker synthesis. The Strecker synthesis is special because not only are we making a carboxylic acid, but it allows us to make an amino acid. Strecker synthesis is special because it allows us to form this carboxylic acid piece, but also this nitrogen. Amino acids, more importantly, these alpha amino acids, everybody should recognize these, right? Alpha amino acids are, why? Why in biology are these important? That's how you make proteins, right? Every single protein is made from some sort of amino acid. Everybody knows, right? You've got chiral amino acids. You guys are made up of a single geometry or chirality of the fundamental 20 amino acids in our system. Why this is so important for synthesis, and what you'll notice too, is if we're working, we are fundamentally made up of all these different proteins. Having the ability to build new alpha amino acids where we change this group here is why the Strecker reaction was built. It allows us to actually come up with semi-synthetic or novel amino acids that either get incorporated into other peptidic drugs or a lot of other biochemical research. So this is a very, very powerful reaction. What you have here is the 3 separate steps to make this reaction. The Strecker reaction, what we call Strecker, is all 3 of these in one shot, in one pot. And the most important thing with this is not a brand new reaction. If you look at this, step 1 here, taking an aldehyde with ammonia and a weak acid to make an imine. Remember this? This is imine formation. This was sort of like lecture what? 3-4. Once you've got an imine or aminium, that aminium can be attacked by cyanide. Cyanide addition to this component to make these alpha amino nitriles. This is like lecture 1, lecture 2. Remember, if we take a carbonyl and we acidify it, we can make these alpha hydroxy nitrile compounds. This is the same version. This is just with your nitrogen. So having an aminium species like this and a weak nucleophile, you remember that activating these carbonyls with these positive charges, it makes the electrophile more reactive. The nitrogen or the negative charge here can attack to make my alpha amino nitrile. That's where I've now brought in this carbon-carbon bond. This carbon-carbon bond brought along with it the C triple bond N. We just have to do this last step, which is the hydrolysis. This is where we have to hydrolyze that C triple N to make our carboxylic acid. So 2 parts. This is a really classic, very important reaction, super, super easy way to take aldehydes, where whatever this R group is here, we can reformat it to make a new carbon-nitrogen bond and a new carbon-carbon bond. But it's just an aggregate of 3 other reactions you guys have seen right now. This is why, again, from a point of strategy for OChem, don't treat this as, oh, it's this whole new reaction we've never seen. No, it's taking 1, 2, 3 steps that we've already built. Imine condensation, nucleophilic addition to a negatively charged or positively charged center. This is no different than the reductive amination that we did. Remember where we use hydride adding to aminium? This is cyanide adding to an aminium in that part. And then the last step is just the hydrolysis. This is what we went through at the end of last class. It's taking this and then doing a hydrolytic cleavage under acidic conditions. So I'm going to walk through the overall mechanism. This is all 3 steps that you guys have seen. It's review from what you guys have seen in the previous ones. Number 1, we take a carbonyl, neutral ammonia. If we attack that center, pop up over here, we make our Zwitter ion. Once we've got our Zwitter ion, we have to do a proton transfer. I've got too many protons on my nucleophile. I'm missing protons on my electrophile. I have my negative charge, and I'm going to pass it over to whatever my weak acid catalyst is. In this case, the system, under acidic conditions like this, usually your proton carrier is going to be your ammonia. That's why when you run these conditions, you typically see them presented as ammonium chloride with ammonia. So the ammonium center is what's holding the proton for the system. We add a proton to this center to give us back our cation. We remove the proton over here. So it's a 1-2 proton transfer to get to your tetrahedral intermediate, this alcohol nitrogen system. Now we're halfway there. To make our imine system, we have to collapse this nitrogen, and we need to kick out this oxygen. So once again, protonate the oxygen with our weak acid. We turn that oxygen to a better leaving group, and then we bring in to make a new nitrogen to carbon pi bond, ejecting that carbon-oxygen bond. That gives us a carbon-nitrogen double bond as our aminium center. This is that first step. This is the same sequence of reactions you did for any imine formation that we've done under these mild acid, mild base conditions. Step 2. Once I've got my aminium and a nucleophile, this is a straight nucleophilic attack into that aminium center. This is the same thing as using the sodium cyanoborohydride. I've got a protonated nitrogen. It's a pretty good electrophile. I got a nucleophile here. So nucleophile comes in. electrophile goes out. Boom, boom, is all that happens. This makes a tetrahedral intermediate as your amino nitrile intermediate. That's what we get to this point here. Usually for this reaction, this is kind of where the whole thing will pause. On workup, or our final step, is we have to do a hydrolysis. So usually, you will run this, you will add ammonium chloride and cyanide together. Everything can condense in, and it will stop and wait here until we're ready for the next step. The final step is this hydrolysis. We take these alpha amino nitrile compounds. Usually we use acidic conditions, so just HCl and water and heat. So this is the same generic substrate we talked about last time from last lecture. Nitriles under these conditions will reformat where we're protonating the nitrogen, we're doing the water addition, and we come out with the carboxylic acid. That carbon right there is the carbon we brought in on the nitrile. So for Strecker, it's just the same substrate, but we have a nitrogen next door. It doesn't impact the overall chemistry. It's just the same as acid-catalyzed nitrile hydrolysis. Now, something I mentioned in last lecture, and I want to put another focus on it. We have two mechanisms for hydrolysis of nitriles, under acidic conditions, under basic conditions. And just like we talked about for like acetal and ketal, acidic conditions or basic conditions are possible. This is absolutely done under acidic conditions. Why is nitrile hydrolysis under acidic conditions better, easier than basic hydrolysis of nitrile compounds? Yeah?
Because the basic, you often stop at the primary amino.
Yes. And again, if you haven't looked at it, haven't watched it, again, I have a YouTube tracking algorithm that shows all this thing, so I know. Go watch that mechanism. I'm putting that spec down that absolutely you have to go check this. Under acidic conditions, the way this reaction or mechanism works is here. We start off with the nitrile. We activate the nitrile to make a positively charged intermediate. If I have a positively charged intermediate like this, water can attack that center to make my first component. I'm going from an SP to an sp2 hybridized system. And again, under acidic conditions, I'm always dealing with these positively charged intermediates. Under basic conditions, these are anionic. And if you try to follow the same sort of mechanism through, you'll get to a system where at some point, you're going to be forcing the system to eject the nitrogen minus, effectively, negatively charged. It just means that under acidic conditions, room temperatures and normal sort of temperatures and pressures, acid hydrolysis is totally feasible. You can do this. Under basic conditions, you're going to need a lot more time, a lot more temperature, a lot more base. You'll probably end up digesting the molecule before you end up hydrolyzing things like the amide. So mechanistically feasible, totally impractical. So what you'll typically see under Strecker conditions, protonation, attack of water, proton transfer, and then another water attacking to give you your tetrahedral intermediate. After that, it's the same sequence that you've seen for imine formation. We have to eject the nitrogen, so we need to add a proton to that nitrogen center. That turns it into a leaving group. We're bringing the oxygen back down. The lone pair on the oxygen reforms my sp2 center and kicks out this nitrogen. That gives me my final leaving group and a final proton protonated system. Dumping that proton just returns the proton to my acid catalyst in the system, and I'm back to my carboxylic acid. So this is something I want you guys to remember. Pay some attention to this. Stop and pause and look at this, because this carbonyl dance, this breathing motion, this is pi bond tai chi. You have to be able to see this as something, no, seriously, it's carbonyl up, carbonyl down, right? This is a very common thing that you see. You'll see this pattern over and over and over again in this class. So this is your time to stop, really make this feel solid, because it's something we're going to keep using again and again. If this is something you're tripping with, it's going to be a problem. The good news is that is midterm cutoff. That is all you have to know for midterm.
So now for this problem, what we're trying to do is find an aldehyde that would give us a racemic synthesis of phenylalanine. That's this molecule here. When we say racemic, we're saying that chiral center, both the R and S and enantiomers are present here, so we're not controlling the stereochemistry. So just working backwards, if you imagine the Strecker synthesis, remember it's the 3 individual steps we discussed. The final step is actually the nitrile hydrolysis, so we're going to just go backwards to the previous molecule. So that would be here. Give you that. Before that, right, the next step back, the penultimate one, is the addition of that nitrile to the aminium. So that would be something like this, plus, and then back one more is the aminium condensation or aminium formation. So that would be this parent aldehyde. So that's the aldehyde you would need in order to install the two groups. To sort of map out the centers, this stereocenter here is that one here, it's this one here, and that there. So when we're drawing this out, the amine and carboxylic acid come in. Amine comes from the ammonia, from the aminium formation, and the carboxylic acid comes in with the nitrile. It makes everything else from the aldehyde. So in a similar question, we're looking for the synthetic pathway to make this one. What are we going to start out with? Like we did in the last question, the amine, remember, that comes in with ammonia, that comes in with the nitrile. This center here is really the masked, or the aldehyde center we would have started out with. So I can start off by drawing that component first. This aldehyde would undergo a reaction with ammonia and NH4, Cl, but we can also use, let's say, sodium cyanide. So this mixture gives us all the components we need. This part here is for imine formation. That's my nucleophilic nitrile component. This first step will get us through to the amino nitrile. Then the way we draw it is step 2 would be our acidic hydrolysis using heat. That will get us the acidic hydrolysis of the nitrile to give us our carboxylic acid.